Hello everybody, my name is Richard Socher and I'm the Chief Scientist at Salesforce and Adjunct Professor at Stanford University. This is an introduction to deep learning for natural language processing, which will get you acquainted with the basics of both deep learning and its applications to problems that involve natural language. At the highest level, natural language processing is a field that combines algorithms and ways of thinking from computer science, linguistics, and artificial intelligence in order to design systems that work with or process natural language, like the one I'm using right now. It's not necessarily our goal to endow machines with a full understanding of language. That's a hard and ill-defined problem, because we have world knowledge and a richness of experience that isn't captured by text or speech alone. And machines just don't understand language the way that we do. Language itself is intertwined with thought, planning, emotions, communication, and the complexity of meaning. In that sense, NLP is AI complete. A full understanding of language would have to capture all the types of intelligence that we exhibit as people, and maybe more. We don't really know how to build such a system. But there are many useful applications of natural language processing that don't necessarily involve the pursuit of general artificial intelligence. Every company communicates with customers using natural language, and there are corresponding NLP tasks that facilitate such communication. Customers often ask complex questions that require knowledge of a company's products and possibly reasoning about that customer's case. To deal with that scenario in NLP, we have question answering models that focus on answering questions over a knowledge base. Customers also speak and read many different languages. So NLP has machine translation tasks that focus on translating from one language to another, like French to German or English to Spanish. Customers leave feedback or submit requests, and in NLP we work on summarization to extract the main takeaways from such longer documents. People want to interact with computers naturally. So in NLP, we build dialogue agents that keep track of user requests and respond accordingly in complex chatbots. The complexity and ambiguity of language can make this difficult. Take, for instance, the simple sentence, "I made her duck." Did you cook her a nice meal, or did she have to duck out of the way? We rely on context to resolve such ambiguities, but much of that context is missing in just raw text. Even for things we do easily, it can be extremely difficult to put into words precisely how we do them. That's the gulf we must bridge between our own understanding of language and the NLP systems that we build. Deep learning will be our tool of choice because it's had the greatest success in solving the problems that humans do so easily and naturally so far, even when we can't quite describe how we do it in our brains. Deep learning is a subset of machine learning, which itself can be seen as a subset of artificial intelligence. All three focus on building models that solve problems using rules and features that they automatically extract from data. The development of deep learning can be seen as the movement away from hand engineering such rules and features to automatically learning them. The key to learning such features and rules automatically is to create well-designed models that consume massive amounts of data. In order for our models to learn useful features, we must provide them with lots of examples of the kinds of decisions we want them to make. To get a sense of how this works, let's consider a simple toy example. Let's say we have a list of words and we want to teach a computer how to identify whether they're positive, negative, or neutral in their sentiment. In both machine learning and deep learning, it's common to represent data points as vectors, or simply lists of numbers. Data points can be anything: images, text documents, or in our simple first use case, just a single word. In this example, each word is represented by a list of two numbers, or what we say a two-dimensional vector. We can also use a deep learning model to learn these numbers and what they should be, but for now let's assume we have already learned them and we're just going to use them. We can visualize these vectors by plotting them in 2D, as you can see here. We then design a model that learns to make decisions about the sentiment of each word, and we can visualize the decisions that our model would make as curves in this 2D space. As you can see, when our model first starts out, it makes quite a few bad decisions. but it will use the words we give it as training examples in order to learn to make better decisions. We'll define a loss function, which is sometimes also called an objective function, that looks at the training examples our algorithm answered incorrectly and gives a score for each one. In this case, let's just say we add a single 1 to the loss for every example the model got wrong. We can then take the total loss and pass that to another algorithm called an optimizer. The optimizer has access to the parameters of the model, which are internal numerical values that affect the behavior of the model. Also, the optimizer changes these parameters to improve the decision making based on the loss. In this case, to reduce the number of incorrectly classified words. Because we provided training examples with 3 different kinds of labels, our model eventually learns these 3 categories of sentiment quite well. We can then test our model on words that were not training samples to see whether it has learned well enough to also work on new, unseen data. Now, in the accompanying notes, you'll dig deeper into how deep learning and NLP actually come together. You'll see how vectors are used throughout deep learning to represent different concepts. And you'll get further acquainted with some of the main NLP tasks that researchers and companies focus on today. Then in the lab, you'll learn the basics of working with text for natural language processing and play around with the basic components of a deep learning framework. Have fun!